So we're on week 15, which is probability. Now the probabilities we do here, nice, hi Jamie, take a seat, are nice and straightforward. They're not complicated, okay? So you won't have to predict the weather, where the government spends millions of pounds trying to work out what the weather's going to do tomorrow and still get it wrong. What we're going to do is we're going to flip coins and roll dice. That's kind of probability at foundation level in maths, yeah? So, everything we've done for the last 3 lessons has been to do with this thing, and it's called the data cycle. It's the reason data exists, okay? So for the last couple of lessons, we go around the data cycle and we find out why we're here. Why are we doing data? Why does data have its own module in the exam? And it's because of this thing, okay? So what kicks off the data cycle? A problem or a question that we need to be answered, yeah? The problem might be, or the question might be, what is the average pay of lecturers at Preston College? So I've got a problem, so what do I do next with my problem on my data cycle? Collect the data, good. Okay, so I've got to go out and I've got to ask the teachers how much they earn with my little questionnaire or whatever it is I've got. Okay, so data exists for a reason. I've collected the data, what do I do next? Good, I process it. And processing was what we did last week, which was all of those displays, bar charts, histograms, frequency polygons, tallies, all of those things fell into stage 3. And then finally, the 4th stage of our data cycle. Solve. You solve it, you answer the question, you compare. Any of those words can go in there, okay? So the reason we have data is because we've got a question. We go out and collect the data. Can you remember how we collect the data? What are the 3 ways of collecting the data? Sort of a table, yeah. It's a bit more structured than that. Good, a questionnaire. So a questionnaire could be a table, they're the same thing. Okay? So we've got a questionnaire, an experiment, and an observation. So a questionnaire is somebody asking you a question, you're standing there outside the canteen and saying, what are you having for lunch? An observation is standing there and watching the number of red cars passing you on the street, and an experiment is actually applicable to probability. That's actually flipping the coin or rolling the dice. So what we're going to do today with probability is we're going to stay in stage 1. And what we talk about is theoretical probability. In other words, what are the chances of rolling a 6? What's the chances of flipping a head? So everything we do today is going to be in here. Tomorrow, the fun stuff. We're going to start rolling dice to collect data, and with probability there is a particular way of displaying the data and processing it. Okay? And that's something called relative frequency. So you calculate a relative frequency and you can plot a relative frequency graph. So that's what we're doing tomorrow. Okay? Good. So out of our objectives, and we've got find learning outcomes today, we're describing and using the vocabulary of probability. Just some fancy words we have to use when we're talking about probability. We're going to look at estimating probability on theoretical models. That's kind of saying, what's the probability of flipping our heads on a coin, that sort of thing. It's the theory behind it, okay? And it is really quite straightforward. So I've got my coin ready, I've got my dice ready. We're going to sort of look at how we calculate probabilities of theory. We're going to look at something called mutual exclusions. Anybody heard of a mutual exclusion before? Mutual exclusions are things like my wife watching a football match. They just don't go together. A mutual exclusion is where things don't get put together. So if I said to you, I want to roll a 7 on a dice, I can't do it because there isn't a 7 on the dice. It's mutually exclusive. Rolling a 7 and this dice are mutually exclusive. Okay? And then the second bit, just Lewis is saying, is that probabilities have to add up to the number 1. Yeah? And we're going to use that to work out missing probabilities. Okay? The 4th thing we're going to do today, so out of our 5 outcomes, we're doing 4 of them in one day, is we're going to list all the outcomes for a single event, in other words rolling a dice, or 2 successive events. So essentially, we're talking about rolling 2 dice. And there's a real basic structured way of doing that. And if you take the structured way for 2 dice, it applies to 2 spinners, 2 coins, different flavours of chocolates, all sorts of questions they're going to ask you. And that's really what we're going to cover today. What we're going to do tomorrow is save the fun stuff, okay, just to make sure you come back. So tomorrow we're rolling the dice. We're going to talk you through the data cycle with respect to probability, and we're going to look at relative frequency and plotting this thing called a relative frequency graph, which is kind of stage 3 on our cycle. So let's start the maths lesson proper. Let's do a smart recap. So what we do, okay? So in weeks 2 and 3, we covered fractions and decimals and percentages. So we're going all the way back to weeks 2 and 3. I'm asking you 3 questions there. 1 minus 3/5, 0.4 plus 0.3, and what is 20% as a decimal and a fraction. And then once you've answered those, I'll relate them to why they're important in today's lesson. Okay, let's go through these then. I've got 1 minus 3/5. So fractions, let's go all the way back to fractions. What's the answer to that? 2/5. I'll put it over here, and if you put it into a calculator, that's good enough in Unit 1. You don't get a mark for showing you're working out in Unit 1 because you've got calculators. But how do I do that? What's the manual way of doing it if I didn't have a calculator?
You need to put 1/5 as well, like 5/5.
Yeah, 5/5. So the number 1 is 5/5 because we know that a fraction is another way of writing a division. So 5 divided by 5 is 1. So what we're trying to do when we do fractions is, just like we did when we had different denominators, the number on the bottom, is you're trying to get the same denominator. So if I force the number 5 to be the denominator for the number 1, then I have to have the number 5 at the top, because 5 divided by 5 gives me the number 1. That's what a fraction is, it's a division. Okay? So 5 over 5 represents 1, and we're going to take 3 over 5. Now we've got like with like, in other words, our denominators are the same, our numbers at the bottom are the same. 5 minus 3 gives me the 2, and then the denominator is still the number 5, okay? 0.4 plus 0.3. Good. If you put it in a calculator and just write the answer down, that's not an issue in Unit 1. If you're doing it in Unit 2 and you have to show you're working out, then the way you add decimals is to use the column method. In other words, line up your decimals and your tenths, and then add them up, and you get 0.7, okay? And then finally, 20% as a decimal and a fraction. So as a decimal, 20% is 0.2. Good. Okay. And as a fraction, 20% means good. Brilliant. 20 over 100. But when I simplify it, breaks down all the way down into 2 over 10, which breaks down to we got there in the end. It's 1 over 5. So okay. Everyone happy with that? So that's going back to weeks 2 or 3. Why is it relevant today? Why am I asking you about fractions, decimals, and percentages? What's the relevance to probability?
Probability is a percentage.
Good. It's a percentage or a fraction or a decimal. So the 3 formats that we talk about with probabilities are fractions, decimals, and percentages. So they have to test you on the basics in all 3 units. So in Unit 1, one of their favourite ways of testing you on fractions, decimals and percentages is with probability questions. And you have to be able to switch between fractions and decimals and percentages. Okay? So there's logic behind their madness. And to clarify the point, when you're doing probability questions, the answer can only be a fraction, a decimal or a percentage. You can't... Anyone heard of the expression, what's the chances of Man United winning this weekend? Oh, it's 50-50. It's not a proportion. You don't talk about probabilities as a ratio or a proportion. It's not 50-50, 20-10 or whatever. A probability is fraction, decimal or percentage. Having said that, we're also going to talk about some words we use in probability as well. Okay, good. So what is probability? What are we covering today? What does it mean? What is it? What's probability? Good. Yeah, that's all it is. It's the chance of something happening, isn't it? Really? So what is the chance of it raining? What's the chance of somebody passing their GCSE exam? I'm not even going to go down that route. Okay? What's the chance of pulling out the 3 of hearts from a selection of cards? That sort of thing. What you need to understand for today is your probabilities are really going to be restricted to these nice basic ones, where we're rolling dice or picking cards or flicking coins. Things like you passing an exam, what's the weather doing tomorrow? There are too many influences that affect what the outcomes are. So we're not doing anything that complicated. We're just going to stick to the real basics today on probability. So we've got this thing called the probability scale. Much like everything else in mathematics, we measure probability. Therefore, just like a ruler, if you're going to measure something, we need a scale. We need to have one end saying something and the other end saying something else. So what do we think this scale goes from and to when we're talking about probability?
Unlikely. No, it's not. It's impossible. Unlikely.
Good.
Even.
Yeah.
Likely.
Good. Got all the good words. And you have to know those words particularly, okay? So if we're talking about the probability scale and they ask you for the words involved in the probability scale, so not fractions or decimals or percentages, these are the exact words you have to use. And they can give you a blank probability scale and ask you to label it. Or they can ask you to circle a probability with words. Now I've got a word of caution when we're talking about words, and that is you only use words to describe probability when the question asks you specifically for words. Okay? So when I come to mark your assignments and your practice papers in a couple of weeks and the rest of it, when it's saying what's the probability of rolling a 6 on a dice, I don't want to see unlikely. I want to see 1/6. Unless the question specifically says what's the probability of rolling a 6 in words, then you'd use unlikely. Okay? But what I find is because we cover these words and people think that's probability, they stop doing the maths and they start introducing the words. So my word of warning to make sure you don't drop marks in the exam, okay, is only give words if you see specifically it asks for words. If it doesn't ask for words, then there's a number involved. And that really is the first objective, as simple as that. What are the words that we associate with the probability scale? Okay? And there's one more word. What's an outcome? We've talked about it a couple of times, we've touched on it a couple of times.
Just what you get at the end.
Good, the results, what you get at the end. So an outcome is what's going to happen at the end. But an outcome could be a specific outcome, or it could be what are all of the outcomes? How many outcomes are there when I roll a dice? 6, yeah. So 6. There are 6 outcomes for a dice. How many outcomes when I flip that coin? 2. Okay. So outcomes can also be the total number of outcomes, or the outcomes we're interested in. When we calculate probability in a minute, we'll be talking about outcomes. Good. Let's move on to the next bit. We've got our probability scale in words, and we've used all our good words, impossible, in evens, and unlikely, and likely, and certain, and all the rest of it. But what did we say were the only units to measure probability?
Percentage.
Percentage, decimal, fractions. Okay, so fractions, decimals, and percentages are the only way that we calculate probabilities. Fractions are most likely to be used in probability because of the way we calculate it. So you can see that when we add up all the probabilities of whatever our outcomes are, they always have to add up to the number 1. And we can use that in maths to find things that are missing with respect to probabilities. And you'll see that in a little while. Good. So, probabilities then. We've said that the way to calculate a probability is what is it that I'm interested in, and then divide it by all of the possible outcomes. Okay? I think in the book it says the outcomes we want divided by all of the possible outcomes. And that's all you really need today. This thing here, this little equation, is going to satisfy anything we do today and tomorrow, because that's as hard as it gets at foundation level. So let's look at the basic way they ask you. The basic way they ask you is with a coin, rolling a die, or picking a card from a pack. Okay? So let's say we've got our coin, and we've just said earlier, if I'm interested in heads and I flip my coin, so I'm flipping my coin, and we stop it, the chance of getting heads, woohoo, is 1/2. One thing I'm interested in out of the 2 possible outcomes. When I roll my dice, what's the probability of rolling a 3? Well, there's only 1 3 on the dice out of 6 possible numbers that could come up. So when I roll it, I should get a 3.
6.
Yet to get one right today. Not had a 3 all day. Okay? Then probability of picking cards. Now, they're not going to expect you to know how many faces there are in a pack of 52 cards or whatever. They're going to reduce it, and they're just going to use cards, and they're going to give you a selection of cards, 3 or 4 of them, and they're going to say, here I've got 4 aces. What's the probability of picking the ace of spades? Well, if you can work out the theoretical probability of doing something, which is what we're doing here. When you actually do it in practice, it's something different. Okay? So these are their favourite ways of testing you on probabilities. Okay? Theory. What's the theory behind it? What am I interested in divided by the number of total outcomes? Other questions they can ask to see if you understand about probabilities will look like this, and I'll leave this up here for you to do for a minute or two, is which of these values could not represent a probability? So look at those values, think about it for a minute or two, and we'll go along and we'll discuss which of these values can and can't represent a probability. Not calculating any probabilities, do I understand the bounds of the probability? So can 0.6 be a probability?
Yes.
Yeah, because it's between 0 and 1. Can 1.2 be a probability?
No.
No. So when football managers say the lads gave 120%, 1.2 is not a probability. Okay, can't be done. Minus 0.5.
No.
No, because it stops at 0, and minus 0.5 on a number line is even further to the left of 0. So that can't be. 4 over 3.
No.
Why can't it be?
Because if you divide 4 and 3,
Yeah.
it's 1 point.
Good, so it's over 1.
Yeah.
What sort of fraction do we call that? Anyone remember? Back to week 2?
I thought it was improper.
Perfect. It's an improper fraction. When it's top heavy, it's an improper fraction, which means it's bigger than 1. And we've already said our probability scale finishes at 1. Can't be. 4 over 5.
Yes.
Oh, sorry, yes it is, just. 4 over 5, yes. Okay? Good. Happy with that? Anybody know what that is as a percentage? Checking that you can switch between fractions and percentages really quickly. What is it as a percentage? What is a percentage out of? Always. 100. So what have I done to get from 5 to 100? What have I multiplied it by?
20.
What do I have to do to the numerator if I multiply the denominator by 20? Yeah? So the quick way to go from a fraction to a percentage is make the denominator 100 and do what we call equivalent fractions. That's what fractions were all about. The most important thing we did on fractions was something called equivalence. So 4 over 5 is exactly the same as 80 over 100, and 80 over 100 means 80% by definition. Okay, good. So, other questions could involve a number line. Okay, so what we've got here are 3 questions, and you have to plot on your probability scale where those letters would be placed. So what is the probability of rolling the number 1 on a 6-sided dice? 1/6, yeah? Happy with that? Interested in one of them? How come I? You'll be sick of dice by the end of today, trust me. Wait till tomorrow when we roll it 60 times, you'll be well bored of them, right? So it's 1/6. So where would 1/6 be? If I've got 0 here and 1 here, where would I label the probability for rolling the number 1 on my scale? Which one would I mark on my scale? So this is trying to show the connection of something we did earlier in numbers and fractions and decimals and representing them as a number scale. So we've done scales in the past, we did scales again last week. So which one of those markers represents 1/6?
The second one after 0.
Good, the second one. So they would expect you to put a little A above that because that represents 1/6. Because it's divided into 6 bits, 1/6 is the first bit. Yeah? Good. Roll a 7.
B.
It would be,
It's like you cannot.
where would I put it?
0.
0. So B would live there because it's impossible. I can't roll a 7 on a 6-sided dice. Roll a number that's less than 7.
C. 1.
It would go all the way up here, 1. Because every number on the dice is less than 7. Okay? Good. So that's deriving and using estimates of measure for probability from theoretical models. So we haven't flipped any coins yet, we haven't rolled any dice, we haven't picked any cards. All we're talking about is theory of probability. Okay? That's what today is all about. Now, we said earlier, probabilities always add up to something. What do they add up to? they always add up to 1. Yeah? So we said earlier when we looked at our 6 numbers on our dice, 1, 6 plus 1, they add up to 1. So knowing that, if we have a probability of something happening, the probability of something not happening is 1 subtract the probability of it happening. Okay? So if we say, what's the probability of rolling a 5 on the dice? You're going to get sick of this, I told you. Is 1/6. Everyone happy with that? Yeah? So the probability of rolling that 5 on the dice is 1/6. What's the probability of not rolling a 5?
5/6.
Good, because the probability has to be adding up to 1. You take away the 1/6 that we know we've got for rolling a 5, and it leaves 5/6. Hence, here's one for you to do, and you probably need a calculator if you haven't got. Basically, we've got the probabilities of somebody spinning a spinner. Everybody happy with a spinner? It's these things you get at fairgrounds where it's got an arrow and it's split into sections, and you've got, depending on the size of the section, that depends on the probability of you getting something. So I spin my arrow round, and it goes round and it stops on a number. Okay. So if somebody's got one of these spinners, and they've worked out the probability of getting 1 is 0.274. The probability of getting a 3 is 0.216, and the probability of getting a 4 is 0.307. What they're asking you is, what is the probability of rolling a 2? Over to you. So, let's do step 1. What's the probabilities of 1, 3 and 4 happening when I add them together?
I just get answer.
0. It's alright, it's only the 4th time I've done it today, I know off the top of my head. Okay, so the probability of 1, 3 or 4 coming out the hat is this plus this plus this. Therefore, we know that the sum of all the probabilities have to add up to 1. So what's the probability of a 2 happening?
1 minus
0.797, which, doing my maths really quickly in my head,
0.203.
my man. Good, man. Yeah. Good. Okay. So, can you see how they can ask you questions on your understanding of probabilities adding up to 1, but in a different way? That's all that's trying to show. Okay? This is a nice simple one. Okay? So the probability that Andy's going to pass his driving test is 0.67. So from that, what's the chance of him failing his driving test?
0.33.
Fantastic. Get that? Right with that, Jamie? Yeah? So if he's going to pass, it's 0.67. 1 minus 0.67, 0.33 is the probability he will fail his driving test. Mutual exclusions. We talked about mutual exclusions earlier. What's a mutual exclusion? Rolling a 7 on a dice. Excellent. Okay? A mutual exclusion is when outcomes cannot happen at the same time, because it's impossible. Okay? So when I've got a pack, I've got 4 cards and they're all 3s. What's the probability of me pulling a 1 out of there? Well, I can't. It's mutually exclusive. How do they test you on mutual exclusions in the exam? Well, it's quite a tricky thing, because they can't just ask you outright what's the definition of a mutual exclusion. You're not expected to know that. A mutual exclusion is matching up a set of rules. Some things adhere to the rule, then they're not mutually exclusive. If something doesn't adhere to a rule, it is mutually exclusive. Let me show you what I mean. One of the ways they've put it in the past in the exam is you've got 6 counters here, and the counters should be paired up. Rolling a number greater than 5, rolling an even number, and rolling an odd number. And they need to be paired with rolling the number 1, rolling a number 6, and rolling the number 4. So we need to pair them. So rolling a number greater than 5 would be paired with what? There's only one possible thing that it can be paired with. Rolling a 6, yeah? Because the only number that's greater than 5 is the number 6. Okay? So this one is mutually exclusive with that one and mutually exclusive with that one. And what they tend to do with these matching exercises to check your understanding of mutual exclusions. So if we talk about rolling an even number, well, I've already matched up the 6, so what can it only be matched up with?
4.
Rolling the 4. And then finally, rolling the number 1 must be left with rolling an odd number. Okay? Now I've done that nice and straightforward in a way that made it quite easier to see what it is. Their first question might be rolling an even number. And if you pair it with the 6, you've then messed up the other one. You see what I'm saying? So you could have done this in a different order, and it could have messed you up. So, and that's the third outcome. We're bombing through these outcomes today, aren't we? Okay, so we've got identify mutual exclusions, things that can't happen together, and the sum of the probabilities has to be 1. So we've talked about equal probabilities. So when I'm rolling my dice or flipping my coin, there's an equal chance of those things happening. The way we calculate unequal probabilities, and the way they ask you in the exams, is jars of sweets, coloured marbles, spinners, dice with 9 sides and different numbers and all the rest of it, is exactly the same as we've done it. What do I want divided by all of the possible outcomes? That's the only thing you have to really remember today with respect to probability. What do I want, what am I interested in, divided by the total number. Okay? So nothing has changed with respect to what we do for probability, whether they're equal or unequal. You just have to be aware that rather than just 1 over something or 2, you've got to take these other numbers into account. So here's one for you to do. A bag contains 6 blue, 5 red and 9 green balls. Balls selected at random, find the probability that the ball is green. So have a go at that one. This one, it's 9 over 20. Everyone happy with that? Can I simplify it? No. Okay, because there isn't a number that goes into 9 and that goes into 20. Good. It's another one for you then. So the probability, where we calculate it, hasn't changed. What's the probability on my spinner of getting a 1 or a 3? Good, so it's a 3, a 3 and a 1. So there are 3 things that I'm interested in on that spinner. I want one of those 3 things. So my numerator is 3, my denominator always is what's the total number of things it could possibly be, which is 8. Can I simplify it? No, because 3 is a prime number, it doesn't go into 8. Don't waste time and brain power in the exam trying to simplify things that don't simplify. Good. Now this is the trickiest bit of today, unfortunately for you, and that is what happens with multiple events. And really at foundation level, we're not going to do this in a clever mathematical way. I'm going to give you a process for doing multiple events. And when we're talking about multiple events, I'm saying to you, rolling 2 dice. Okay, so roll the dice. How many different combinations are there when I roll 2 dice onto the table? What sort of numbers come up? Is there a good way of doing it so that I get every single combination? 1 and 1. So what you need is a structured process, a neat and tidy process to write down all the options. They're not going to ask you to do that. Okay? When they have the 2 dice scenario for multiple events, you haven't got the time and they haven't got the marks to get you to fill that from scratch. Because it would take you 10 minutes, it would be worth 10 marks, and the exam's only got 54 marks in it, and they can't allocate 10 marks to just one topic or one question. Okay? So what they will do is they'll do it for you. So when you look at the 2 numbers on the dice and we add them together, and the reason I'm showing you this is their favourite way of asking you about multiple events, is 2 dice being rolled, and they'll give you a table, and I fill the whole thing. But for you, they'll leave out a gap of this little corner and get you to fill 2 or 3 of them in for a mark. Okay? And what this table shows is a red dice and a green dice, and the results when I roll the dice and I add the 2 numbers together. So in this instance, if I roll the dice, it would be adding 4 and 5. So it would be 4 on one dice, 5 on the other, with a total of 9. So what they like doing in these types of multiple outcome questions is they like to see it as a table and get you to finish the table. What they then go on and do, so finishing the table won't have many marks because you'll have sussed out, oh, you're just adding this to that, is to go on and ask you questions to do with probabilities and this. And the questions will be along the lines of, what is the total number of outcomes? So when I roll 2 dice, how many outcomes are there? 36. Brilliant. Can everyone see why there are 36? It's a 6 by 6 grid. So there are 36 possible numbers. So when I roll these 2 dice, there are 36 possible combinations of numbers on the 2 coloured dice. Okay? And that's what this shows. So they're asking you, do you understand what this means? And it's saying every single combination is up there. So whatever we do now to do with probability and this, the denominator, the total number of outcomes, is always 36. Good. So let's now look at some of the questions they ask specifically on this grid. The question might be, what is the number that occurs the most? So what's the most likely number when I roll two dice together? What's the number that's going to most likely to occur? Good. Now, the reason you got 7 is because I colour-coded my dice rolls. 7 is the most likely number. How many? What's the probability of me getting a 7? Out of? Good. So don't forget, it's always a fraction. The probability isn't the number 6. It's 6 out of a possible 36. When we simplify it, we get 1 over 6. Because 6 goes into 6 once, 6 goes into 36 6 times. Yeah? So when I'm rolling two dice, the most likely number is the number 7, and the probability of rolling a 7 is 1 in 6. So here we go. Oh, 1 in 6 counts. Come on, do it for me. Oh, no. Okay. So that's the most likely number. When you see this question in the exam paper, if it comes up, a lot of people get confused because of this 6 and this 6. And you won't believe how many past papers and assignments I mark, and people say the most common number is the number 6. Because they're taking this 6 into account and this 6 into account. Can you see on the diagonal? If I hadn't coloured them red and green, put everything in black, which your exam paper is nothing but black, people are confusing these two 6s and saying 6 is the most likely outcome. You see what I'm saying? I've been kind to you. I colour-coded mine so that you wouldn't say 6. But in the exam, everything is black. It's all the same font. I've even changed the font so it looks different. Okay? And when you say, what's the most popular number? 8 out of 10 people will say 6. Because they're following the diagonal all the way from top to bottom. You have to remember, this represents the dice. This represents the dice. Okay? So other questions they might ask could be along the lines of, what's the probability of rolling a 5? Good. There are 4 5s, 1, 2, 3, 4 of them, and the total number of outcomes is still 36. Nothing's changed there. And when I simplify it, 1 over 9. Yeah. Another question might be, what's the probability of rolling a number less than 4?
3.
Can you see how that works? Because the only numbers that are less than 4 are 2 and 3. And there's 3 numbers that are less than 4. 3 over 36. Good. Can you see how that works? So this combination of events, this 2 dice scenario, is just one way that they can test you on multiple events. Okay, and we've just covered all of those except for maybe the 10 one. Now the other way they might ask you the question is, you're at the fairground and they have one of these spinners. Now I'm going to take you back to week 1 now. And when they have a spinner with fewer numbers, they might leave the table empty. So if I said to you, you have to populate the table with the product of the 2 numbers. Let's just say, let's make it easier. Let's say there are 2 spinners. Spinner number 1 and spinner number 2. And I spin the 2 spinners, and this is spinner number 1 and this is spinner number 2. And it tells you to complete the table with the product of the 2 numbers. 3 marks for filling that. What are you going to put in there? And there's a bit of a lesson in what I'm telling you now. What's the product of the 2 numbers? Can you see how important buzzwords are in GCSE maths? If you don't know what the product means, you can't answer a question that has 3 or 4 marks associated with it. If we go back to week 1 and some of the terminology we used in week 1, and don't worry, I'll give you a glossary of all these words. I think you've got one anyway off Molly, yeah, like a list of words. The product means what? Can anyone remember what a product is? It's the result of multiplying 2 numbers. If I said, what's the sum of 2 numbers? What's the sum of 3 and 4? You'd say 7. because sum, you know, means add up. The product of two numbers, the product of 3 and 4, is multiply 3 and 4 together. So this is a perfect example where, if you can't get your head around the buzzwords, which is why we always talk about the buzzwords at the end of the lesson, you can't answer the question. So here what they're asking you to do is they're asking you to multiply the two numbers. That's what product means. What is the product of two numbers? It's the result of multiplying them. So 1 times 1, 2, 3 and 4. 2 times 1, 2, 3 and 4. 3 times 1, 2, 3 and 4. And then finally 4 times 1, 2, 3 and 4. So really what they're after for 2 or 3 marks is a table that looks like that. And if you don't understand what the product of two numbers is, you can't even begin to answer it, and you've lost 3 marks for doing what I've just done there. Okay? What makes it worse is there will be subsequent questions about that table. What is the probability that I will get a product of 6? So think about it for a second, don't shout out the answer. So what is the probability on that table there that I will have a product of 6? Good man. Can everyone see that? Yeah? The product of 6 means I've got 2 6s on my table. And what's the total number of numbers I have on my table? Well, it's a 4 by 4 grid. So there are 16 possible outcomes. Fantastic. And then where do I go from there? Yeah, always simplify. So in the exam, if you ever end up with 2 over 16, as a natural thing in exams, you always give it in its lowest terms. So simplify every opportunity you get. So I've taught my lot ever since day one. Always simplify fractions if you can simplify them. Good. Okay, not far now, honest. Right. How else can they ask you these questions about multiple outcomes? Okay, so I don't know why, I think they're sponsored by my wife, but a lot of questions you get in the exams with multiple outcomes involve chocolates, and either flavours of chocolates or sizes of chocolates or whatever. Now, just like when we're rolling the dice or spinning our spinners, the way to make sure you get every single combination of these things down is to set it out as a table. So here, they're telling me I've got white chocolate, milk chocolate, and dark chocolate, and I've got 4 flavours of various chocolates. I've got orange, raspberry, strawberry, and coffee. And I would always set it out like this so that I don't miss anything when I'm writing them down. What I find is when you get these types of questions in the exam, you'll get Joe Bloggs and he'll go white milk, white orange, dark strawberry, and he'll just randomly start writing things down because he's trying to do it all in his head. So my advice with multiple events, multiple things, like 2 dice, 2 spinners, types of chocolates and flavours of chocolates, is to do this, and you'll get enough space on your exam paper to do this. Okay? And then just do it systematically. White orange, white raspberry, white, okay? Milk, orange, and do it in a systematic way, like I've shown you there, and then you never miss anything. Okay? So I'm going to give you a couple of questions from exams so that you can practice this process. And this is the trickiest thing you're going to do today. Okay? So here's a question from Unit 1 March 2011. I'll put it sideways because it's not enough room across the top. And I've got 3 types of chocolate. Okay, sponsored by Cadbury's at all of the AQA exams. I've got milk chocolate, dark chocolate, and white chocolate. But this time we're talking about chocolate eggs, which can be small, large, or king size. For 3 marks, I'd like you to write down every combination of types of chocolate against the size of the eggs. Yeah, got all your combinations? Good. And it's nice to see you've all done exactly what I did. Just write it down on the table and you won't miss anything. Because there's always a follow-up question. So here, still got the same question, it's just part B. Okay? It says a box contains an equal number of each egg. 1 egg is chosen at random. What's the probability that it's going to be a small milk chocolate egg? So you always get follow-up questions on those tables. So what's the probability it's going to be a small milk chocolate one?
1 over 9.
Okay, how'd you get that, Lasma?
Because they multiply 3.
Yeah. So the total number of outcomes is
9.
9 from the tables that you've all done. I've seen them all and they're all correct. And then I'm interested in
Small milk.
1 of those combinations. Small milk, that's the only one in there. Okay, good. So it's 1/9. So can you see 4 marks for a nice easy table and a simple question on probability. Good, good, good. This is your last question of the day, honest, just to see how you've understood it. So this guy, Gareth, he goes to a drinks machine, and the drink only dispenses tea, coffee or soup. So when he goes to the machine, he puts his first lot of money in, and he's going to get a tea, coffee or soup. He's then going to put his money in again, and he's either going to get a tea, coffee or soup. So the first part of the question says, list all of the combinations that he's going to get with those two drinks. Okay? And then the second part of the question says, what's the probability that he's going to get two drinks at the same? He's going to get 2 coffees or 2 teas or 2 soups. Like I say, today we've done 4 of the outcomes because they're straightforward. Everything we've done today is theory. Yeah, we've not rolled the dice, not flipped the coins or done anything like that. We're saving that for tomorrow. Right, so we're going to move on to the tricky maths today. This is a tricky maths alert because this is the C grade questions. Working out the probability of rolling a dice or flipping a coin, trust me, that's EF level question. This is where you get the marks. This is the difference between getting a C and a D grade. Okay? And we're going to look at experiments, okay, and frequencies. So, theories and experiments. In the real world, what's a theory? I've got a theory, but I'm not going to be watching the football tonight. What's theory? Sorry, it's an idea. So it's something that's not yet happened. Yeah. A theory is I think something's going to happen, but I haven't checked it. What's an experiment? A test. Don't forget, it's like one of our 3 ways of collecting data. 3 ways of collecting data: experiment, observation, and questionnaire. Good. Okay. So even within our data cycle, experiment falls within the data cycle. Okay. So theory is what I expect to happen. Okay. So theory is what we've just been doing with probability. The theory is when I roll a coin and I'm expecting to get a 5, it's 1 chance in 6. 1/6. That's theory. I actually haven't done it yet. I haven't rolled the dice. So when we're talking about probabilities yesterday and what we've done this morning, most of it, 99.99%, is in theory. Okay? An experiment is what actually happens. I'm going to get my dice and I'm going to roll it to see if I get that number 5. Okay? In order to check if I get the number 5, I don't roll it the once, do I? How many times do I roll it? 6? Yeah. So how many times would you expect to see it if I rolled it 6 times? Once. What if I rolled it 60 times? How many times would I expect to see it? 10 times. Good. That is theoretical probability and expected frequencies, and that's what we're going to talk about now. So we know what our data cycle is. We covered it as part of the warm-up. Okay? We know there's a problem. So theory lives in here. Is my dice a fair dice? Will I get a 5 once every 6 rolls, or 10 times every 60 rolls? So what do? I collect it. I roll my dice and I keep a check of what I'm getting. And then finally, processing and presenting it, we've got to work out some statistics, some numbers, or a display where we can show whether this is a fair dice or not. And that's really what we're going to do this morning. Okay? Good. So we've done theory to death. So let's use a simple example and ramp it up a little bit for our practical test that I'll get you to do. Okay? So we know our probability is the number of the outcomes we're interested in divided by the total number of outcomes. Okay? That's theory. That's a theoretical probability. And that's what you've dealt in yesterday, and generally that's what you're dealing in today. So let's look at a nice simple example. Let's talk about our coin then. So I've got a coin, it's got 2 sides, and I'm interested in heads. So theory tells me the chance of flipping a heads is 1/2. I've got 1 chance over 2. So 0.5, 1/2, 50%, all the same thing. That's the probability of getting a heads. Okay? So expected frequency, so I still haven't flipped my coin, says exactly what we've just done just now. If I flip this coin 10 times, how many times would I expect to see heads? 5. Because my probability is a half that I'm going to get heads multiplied by the number of times I've done it. That's what you've just done in your heads. Yeah? My probability times the number of times I do something. Okay. So you've got an expected frequency. So if I flip a coin 80 times, how many times would I expect to get tails? 40. Because what you're doing is you're saying your chance of getting a heads is 0.5, and I'm multiplying it by 80 to give me my 40. Nice round numbers at this moment. You're going to get hard numbers in a minute. You're going to do your own experiment. Okay? I've got a dice, and I roll a dice 30 times. How many times would I expect to roll a 2?
5.
Wow, that's quick, Morgan. That's really quick. How did you get that?
Well, I worked out that 6 goes into 30 5 times.
Brilliant. So the maths behind it is, what's the probability of rolling a 2 on a dice?
2006.
Sorry?
2006.
How many 2s are there on a dice? So it's 1.
1 out of 6.
1 out of 6 times the 30 times I roll the dice. And what Morgan was doing was exactly what I taught you to do in week 2 when you have a fraction of an amount. Just move that over there and divide 30 by 6 to give you the 5 that he came up with in about 2 seconds flat. Okay. So that's all there is to it. It's your probability times the number of times you do something. So that's what we call expected frequency. And all that happens in stage 1. I haven't rolled a dice, I haven't done my experiment. I'm talking stage 1 here. Okay? So that's where this lives. Theoretical probability, expected frequency is up there. I haven't actually gone around and collected anything yet. Okay? So I then do my experiment. I get my coin out and I flip it 10 times, 20 times or whatever. And I keep account of the number of heads I get. And when I'm doing that, I could use a tally, I could just use a little tick box, whatever you want, put little H's down. I flip the coin 10 times, I only get heads 3 times. So that's the result of my experiment. That is stage 2 done. I need to do something with that now. So my experiment, when I flip my coin, has said I got 3 heads. I now need to take that information and process it. I need to do something with it. And there's 2 ways you process it, with numbers or with a graph. Okay? So let's look at numbers. And the numbers are called relative frequency. It's a posh way for saying what actually happened when I flipped the coin or rolled the dice or picked the cards. Okay? So all relative frequency is in probability. It's what actually happened when I did something. So it's a fancy way, what happened. Sometimes called experimental probability, but as far as you're concerned for the exam, your buzzword is relative frequency. What happened when I rolled the dice? What happened when I flipped that coin? In order to calculate the relative frequency, you just use the information you collected in your experiment. So in the instance of my coin flipping, I got heads 3 times out of 10. So my relative frequency for flipping heads is 3 divided by 10. So that's 0.3. Can everyone see that? So relative frequency isn't some magical number that you invent or some complicated math. It's saying what happened in my experiment, use the numbers from your experiment and say, I got 3 heads, I flipped the coin 10 times, therefore my relative frequency is 3 divided by 10. Everyone happy with that? Yeah? It's not hard, it's processing the data from your experiment. Okay? So relative frequency, the number of times you do something. Essentially, the probability from the number of times that you carried out the test. Okay? I've put here that relative frequency in the exam is normally in decimal format. It's why I said 0.3 rather than 3/10. Because you can then go away and put it on a graph. And you plot the number of times you've done something against your relative frequency, which we'll look at in about 5 minutes. Okay? So there you go. If I flip a coin 20 times and I get 8 heads, what's the relative frequency for getting heads? What's my relative frequency for that then?
20 divided by 8.
20 divided by 8? You mean the other way
Yeah,
around?
other way around.
Other way around. Yeah, I got 8 heads. I flipped the coin 20 times. I can simplify it down to 2/5, or if I want to use a decimal, 0.4, same thing, okay? But generally they'll ask you for a decimal, and they won't give you nice round numbers. You'll be using your calculators in a minute, because I'm going to give you an experiment to do. Okay? Good. So let's talk about relative frequency again then. I roll a dice 50 times and I get a 3, the number 3, a total of 8 times. What's the relative frequency of rolling a 3? Yeah. It happened 8 times out of 50 rolls. What's that? Simplified. 4 out of 25. So that's as a fraction. What is it as a decimal?
4.8.
Multiply this by 4 to get 100. Multiply that by 4, you get 16. So it's 16 over 100, which is 0.16. Okay? You can use calculators. You've got to get your calculators out for this exam. Good. What's the theoretical probability of rolling a 6? Sorry, of rolling the 3. So this is what actually happened in the experiment. If we go back to stage 1, what's the theoretical probability of rolling a 3 on a dice?
1 out of 6.
Yeah, 1 out of 6. And what's that as a decimal? We did it at the start of the lesson. 0.166666 recurring. That's why I asked you in the Smart Starter. Okay? So 1/6 is not... So it's pretty damn accurate, isn't it? It's what I would expect. I can compare my theory to my experiment, and it's the right result. See what I'm saying? Yeah? So when we talked about flicking a coin 10 times and expecting to see heads 5 times, if I see it 3 times, there's something wrong, isn't there? Yeah. Good. So, as the process works then, let's talk about our coin flipping exercise. My theory says my probability of getting heads is a half. I flip the coin 10 times, and my expected frequency says I should see heads 5 times. I only saw it 3 times when I went to my experiment, and my relative frequency says it's 0.3. It's not the 0.5 I was expecting. I discussed the results. It's not the result I was expecting. I was expecting 0.5, but I got 0.3. I get back here. How could I make the experiment better? Do it again and do what? Do it more times. So 10 times isn't enough. If I do it 50 times or 100 times or 1,000 times, I would expect to see heads 500 times out of 1,000. Yeah? The relative frequency would be a lot closer to the expected frequency. Okay? So this is what we've just done. Stage 1, the theory, is the theoretical probability. When I flip my coin, I expect a probability of 0.5, an experimental probability of 0.5. If I was going to flip the coin 10 times 0.5 says I would expect to see heads 5 times. Okay? I do my experiment and I only count 3 heads. I work out my relative frequency of 0.3 and I come to discuss my results. I was expecting 0.5, I got 0.3. It wasn't what I was expecting, but I could make things better by going around my data cycle again, and instead of flipping it 10 times, I flip it 100 or 1,000. Yeah? See how that works. Good. Good, good, good. So let's show you in a random practical way. Okay? Just going to quickly talk you through those processes, something different. Got 5 cards, got 4 aces, and a joker, nice colourful joker. Okay? So, shuffle the cards up. The theoretical probability. What's the probability that when Lasma picks a card, it's going to be a joker? 1 out of 5, because I've got 1 card I'm interested out of the 5 cards in my pack. Okay? So I'm going to do this, let's say 10 times. How many times would you expect to see the joker in 10 picks? 2. Yeah, if it's 1 in 5, then it'll be 2 in 10. So my expected frequency is twice. It's 1/5 times my 10 goes, which is twice. Pick a card.
Yes.
4 times in 10 goes. Okay. So, as far as our tally is concerned, our experiment, we got 4 jokers in 10 attempts. So what's my relative frequency? 4 over 10 or 2 over 5. So what's my discussion going to say? What's my What conclusion do I draw from that? What was I expecting? 1 over 5. Yeah, I was expecting 2 and I got 4. So what can I say about it? Lots more goes. With an experiment, the data is better the more goes you have. Okay? So, discuss the results. The outcomes weren't as expected. I was expecting a fifth and I got 2/5. So at the end of the day, how do I make it better? I go around my data cycle again. It wasn't what I was expecting. So instead of doing it 10 times, we had time, we do it 1,000 times. And what you would find is it would get a lot closer. And I'm going to show you how to show that in an experiment, okay? I'm going to get you to do an experiment now, okay? I've got an experimental sheet here, and it's going to get you to roll a dice. And you're going to go through the 4 stages of the data cycle with your own experiment. The first thing you can do is, if you look at your stage 1 questions, what's the theoretical probability? 1/6. What's the probability of rolling a 4? You should all have 10. You're expecting to see a 4 10 times. You haven't done the second question on the starter. What you can do, even before we start plotting graphs, is that you can see, did it happen 10 times for you? Well, 1, 2, 3, 4, 5. Some people are low, other people are really high. You finished your rolls off. Okay? Other people, so the first thing you can compare is that. What they want you to do next is plot what we call a relative frequency graph. Okay? So what a relative frequency graph shows is the relative frequency against each of your flips of the coin or rolls of the dice. And that's why I got you to do them in groups of 10. Okay? So what you have is we're rolling a dice, and on this instance, on this graph, we've been counting how many 2s that we've got. So the number of 2s is here and the relative frequency is there. Do it on paper, it's a lot more. The point of getting you to plot a relative frequency graph, we know you can see your results based on your frequency table, and you were expecting to see 10 4s, but some of you have got 13, others have got 5 or whatever, is the fact that they want you to draw this. Now this is really important. This is a relative frequency graph. And what it does is it plots your groups of 10 rolls of the dice. And here, this guy was counting the number of 2s he got on the dice. 10 rolls, his relative frequency was 0.1. 20 rolls, his relative frequency was 0.25. Okay? This graph is really important because this graph only ever goes one of 2 ways. This graph is either like this or it goes like this. And you're going to plot your graph in a minute, and hopefully it might look, if you're lucky, something like that. Okay? Why does it look like that? This is a question in the exam. Okay? So they might ask you a question to work out a relative frequency of something. They will then give you a graph and ask you to plot it, and it will look like that. And the final question will be, why does it look like that? This is the really important bit. This proves that the more times you do an experiment, the better the data. When I roll a dice, what's the probability of rolling the number 2? 1 out of 6, 1 over 6, like it's been all lesson like it was all day yesterday. What's that as a decimal? Did we say at the start of the lesson? 1 divided by 6, 0.166. When you do an experiment, at the start of the experiment, your data is all over the place. But here, this guy rolled the dice over 100 times. When he started getting to around 100, can you see what happens to the line? It straightens out. So if I kind of draw a line over there, guess what number it gets really close to when it starts settling out? 0.166. Yeah? This graph, this relative frequency graph, is really important if it comes up, doesn't always come up, because it shows that the more times you do an experiment, the better the information. So finishing off, you should have a relative frequency graph, hopefully, but it does this, or it does, the other way around. That. Whatever happens, wherever it settles out, should be around 0.16, because that's the probability we were expecting to see. If you didn't get that, it's not the end of the world. All it means is we haven't done the experiment enough times and we need to go around our data cycle again. Okay? We're not going to do an extra one because we're running out of time. Okay? So, things to remember about experiments. 3 important points. The more times you do an experiment, the more accurate the probability. So when you're looking at your relative frequency graph, it's off to the right. It's where it starts flattening out, where you expect it to flatten out. If an experiment is repeated, the outcomes are going to be different. So if we started you all off with fresh sheets of paper and I got you to roll the dice 60 times again, what you write down would be totally different to what you've got now. Catch my drift? They've got no memory. Yeah? Finally, experiments have a lack of memory. So the way they ask you the question in the exam is, I've got an experiment, I'm trying to work out if my coin is a fair coin. And I flip it 5 times and I get 5 heads. What's the probability that it's going to be heads on that 6th flip? 1 over 2. Because the last 5 flips have got nothing to do with this one. I'm still interested in one outcome out of a possible 2 outcomes. Yeah? See how that works. As far as yesterday's and today's objectives on probabilities are concerned, we've done everything. Yesterday was the basics on what am I interested in divided by all of the outcomes. That only got complicated when we introduced 2 dice instead of 1. Today was the complicated bit about theory, experiment and relative frequency to show that when I actually roll the dice or flip the coin, how do I process that data?